So if we take a region and divide it into 5 intervals, this is what my region will look like. If you see, I have the 2/5, 4, 6, 8/5, and the 10/5. And as I explained earlier, we have 2/5 times 1, 2/5 times 2, 2/5 times 3, 2/5 times 4, and 2/5 times 5. But it's nice for you to see them this way, because later on we're gonna have to be using that way. So what is the right endpoint? So again, this is the problem. We have our function given negative x squared plus 5. We want to go from x equals 0 to x equals 2, and we only want to use 5 rectangles, right? And the very first thing ever, always go ahead and find your delta x. What is going to be the width of each rectangle? Well, remember, it was going to be b minus a over n. In this case, my b is 2 minus 0 over 5, which is 2/5. So now I know the value of all my delta x's. The value of all my delta x's is 2/5. Well, let's go ahead and find the right endpoint. Ta-da! The right endpoint is going to be given by this sum, the summation of all the rectangles: rectangle 1, rectangle 2, and rectangle 3, and rectangle 4, and rectangle 5, but using the right endpoint. So let's see. As we said, all of them are going to have 2/5. The first rectangle, the base is 2/5. Well, what is the height? The height on the first rectangle, if we're using the right endpoint, the height is going to be determined by this one on the first rectangle, where the height is going to be f of 2/5. So that's what this will look like. There it is. Plus, on my second rectangle, again, the base does not change. It's 2/5. But what is going to determine the height of that second rectangle? The height of the second rectangle on this interval is going to be determined by the right endpoint. If we go up here, this is f of 4/5. That's what we have, f of 4/5 as well here. Plus, so on. Notice the very last rectangle. This is my last rectangle. Again, the base does not change. It's delta x. Well, the height changes, and we're using the right endpoint, and it's going to be this as value, which is f of 2. It's right here. We have the first rectangle, the second, the third, the fourth, and the fifth. If we go ahead and add them, right, this is our notation for summation. If we add them all, we get a value of, I don't know yet. Let's see, how do we evaluate f of 2/5? Well, remember, we are given our function negative x squared plus 5. Well, to evaluate that, we just substituted whatever this x was. So x negative 2/5 squared plus 5. 2/5 is 4 over 25. Negative 4 over 25 plus 5 is negative 4 over 25 plus 125 over 5, which turns out to be 121 over 25, which is equal to 4.84. That is the height for the first rectangle only. We have to calculate the same way the height for all the other rectangles. Once you have your numbers, then you could plug them into here and get a nice summation for a grand total of 6.48. Using the right endpoint, the sum is 6.48. Well, check this out. I want you to see this right now. We're going to be using this notation in the next section. By the way, once you find this 648, you're done. All right, once you calculated all the summation of that and in your function, you are done with the problem. I want you to see this very last part. This very last part is what we're going to be using, all right, later on. For now, you just have to calculate, do the algebra. But here, this is what it means. How do we find the area of that region by calculating? Well, this is saying let's add up. What? Let's add up all the rectangles. What rectangles? All the rectangles formed from that interval 1 all the way to the 5th interval. Remember, we're doing n equals 5, all right? Students say, oh, we're going to x equals 2. Let me make that a 2. No, it's n. Well, of what? Well, I'm gonna be adding up all my rectangles. Well, what is going to be the area of each rectangle? The area of each rectangle is going to be 2/5, the base, times the height. And the height, what is going to be the height? Well, for like 2/5 times I is the interval. Notice why I. If I'm talking about if we're using right endpoint and we're talking about the first interval, f of what? F of 2/5 times 1. If I'm talking about the second interval, that's this x value that is going to be serving as my height. Well, that is 2/5 times 2. F of 2/5 times 2. F of 2/5 times 3. F of 2/5 times 4. And f of 2/5 times 5. Right. So it becomes f of 2/5 times I. and this is going to determine our height, which is 6.48. So how do we do it using the left endpoint? All right, with the left endpoint, we want to use 5 rectangles. Again, b minus a over n, in this case is 2 minus 0 over 5 and 2/5. Well, guess what? Whether we're using the right endpoint or the left endpoint, it did not matter. Delta x was the same. What is going to change is the height of each rectangle. So let's see. Left endpoint, the summation is going to be equal. The first rectangle, let's talk about the first rectangle. It's going to be delta x times f of what? F of this one? No, that'll be the right endpoint. F of this one. And what is this? 0. That is f of 0. Plus, well, my second rectangle, delta x is still the same. Delta x times f of, well, if I'm using the left endpoint for this second rectangle, it has to be this one. 2/5 times 1, right? Plus delta x times f of, I'm talking about this third interval, I'm using this left endpoint, 2/5 times 2, plus delta x times f of 2/5 times, we're using the left endpoint, times 3, plus, so we have 1, 2, 3, 4. I'm coming to my last rectangle, and this is the last rectangle that I always have to pay special attention. Well, delta x is still the same, times f of what? Well, on my last interval, if I'm using the left endpoint, I'm using this baby right here, so it's 2/5 times 4. 2/5 times 4. And what do we get here? You do that. So after you calculate that, we end up with this conclusion, and this is really nice. All right, we end up that the one that was an underestimate, the estimation was 6.48. The one that was an overestimate, the estimation was 8.08. Well, we're using the Archimedes method of exhaustion. It must mean that the actual area is between the inscribed and the circumscribed area. All right, and that is the principle. But what is the actual area? That's what we're interested. Well, if we increase the number of rectangles that we use, the little space between the rectangle and our curve becomes smaller and smaller and smaller. So by increasing the number of rectangles, we're actually increasing the accuracy of our area estimate. So we know that the area of the region, if we use 25 rectangles, for example, nobody's actually going to sit down and calculate 25 rectangles and add them all up. But we know that the area using the area estimate, it's an estimate, using 25 rectangles is somewhere between 7.1, this one. Right, so the range of the area is becoming smaller and smaller as we increase this number of rectangles. So this is going back to what I talked earlier about inscribed areas versus circumscribed areas, and how some books call it the upper sum or the lower sum. I like to go by the right endpoint sum and the left endpoint sum, and then once you have that, then you look at it. Well, was it an overestimate or was it an underestimate? So this is what inscribed areas with a lower sum look like. Well, this is what circumscribed areas look like. And in this case, you will see why I don't like it to call it the upper sum or the lower sum. I like to first determine, use it if it's a right end sum or a left end sum, and then determine based on that if it was an upper estimate or a lower estimate. For example, in this interval right here, if we decide to do a left endpoint rectangle, my left endpoint rectangle, is right here. All right, if we were to continue doing this, and left endpoints, left endpoints, left endpoints, left endpoints. Notice what happens here. It was an underestimate. Left endpoints, left endpoints. As soon as my graph starts decreasing, if I use the left endpoint, it becomes an overestimate. But as soon as my graph starts increasing, the left endpoint becomes an underestimate. What about the right endpoint? Well, the right endpoint here, if we would use the right endpoint here, the right endpoint, 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 See, now we reverse it. See, we use the right endpoint on this one. If we're using the right endpoint, now we're getting over it. So it varies. It's nice for you to practice. So go ahead and take a few minutes to practice drawing your left endpoint and your right endpoint summation. So notation. This is the very last thing that I want to cover for this one. What is the notation? For a lower sum, we use lower s of n, and we say the summation of all your rectangles is equal to f of mi times delta x. Remember, this is saying add up all your rectangles. Well, the area of each rectangle is going to be equal to delta x, which we know how to calculate, b minus a over n, I'm sorry. And then f of mi is the minimum value of f on an interval I. So because we're using the lower value of y. Upper sum, well, the interval from I equals 1 to n of f of mi times delta x. In this case, mi is the maximum value of f on an ith interval. So what is the conclusion by this? That the actual area of any region is always going to be in between two areas. Which area? The area estimate using a lower sum and the area estimate using an upper sum. And well, what happens if the number of rectangles that we're drawing increases? We said that the area increases in accuracy. Well, guess what? If we let the number n rectangles increase all the way to infinity, there's a really nice math property that says that we not only get an estimate, but we actually get the actual area. So what does that become? That means that the limit of the lower sum as n goes to infinity is supposedly less than the actual area, all right, which is less than the limit using the upper sum. Well, the limit, the area is already established. That is a number. Well, we still end up with the actual area. The limit of a number is a number itself, so the actual area is equal to the limit as n goes to infinity of the upper sum, or the limit as n goes to infinity of the lower sum. Because remember, n is increasing to infinity, so we are either getting really close from the upper side or really close from the lower side, but eventually as n goes to infinity, we actually get to the number of the area exactly. So limits, once again, yay, they didn't go away, and they come back again in this section in the next problems.